Hey engineers, and welcome to 1.1.1, Part A, Part 2. And we're going to talk about the wheel and axle and pulley. In Part 1, we went through a lever, and we talked about the three different types of levers. We talked about actual mechanical advantage. Am I free? It's the forces. Ideal mechanical advantage, which is distances. We talked about mechanical advantage, 1 being the magic number. If you're bigger than 1, that means you've got a force multiplier. You can multiply. You put 1 pound in, you get 10 pounds out. If the mechanical advantage is less than 1, it's a distance multiplier. So you put in 1 foot, but then you get 10 feet out. But we learned that the work is always the same. So if you have a force multiplier, you're going to put lots of distance in to make up for that. If you're a distance multiplier, you got to put lots of force in to counteract that. And my example kind of is a scissors. So this is a distance multiplier. I only move this type of scissors, because it's got such long shears to it. So I move this up and down a little bit, and the ends go really far. If I could have scissors that are very small, and they're a force multiplier, so I can cut really heavy material. So that's the idea of, even though this is a distance multiplier, I have to exert a lot of force to make that work. We talked about, let's see, our different types of levers: first class, second class, third class. First class was like a seesaw, second class was like a wheelbarrow, and third class is like a spoon that you'd fling where the pivot's on the center and the effort force is in the middle. And then we're going to talk today about wheel and axle. A wheel and axle. So a wheel and axle, it's funny that they give this example as a wheel and axle, because there's a wheel right here, and there's an axle right there. So another good example of a wheel and axle is a screwdriver. A screwdriver, when you put a screwdriver in and then you turn it, if you've got a larger diameter object that you're turning and there's a smaller shaft, you can have mechanical advantages bigger than 1 or less than 1. Like this example here with the tire, you're turning the shaft, which turns a larger tire, which is different than a screwdriver. On a screwdriver, you turn the larger shaft, which then turns the smaller one. Now, it's cool, like in hybrid cars, you get both of these. So when you push on the gas pedal, the engine turns the axle, which then turns the wheel. But then when you hit the brakes, the wheels will recharge the battery by using the momentum of the car to then turn the shaft. So it's one time you're the one turning the shaft, and the other time the shaft is the one getting turned. So here's other examples where you grab the large steering wheel, grab the large outside, which turns the shaft, grab the large outside, turns the shaft. This is a faucet on the outside of your house, grab the large inside, turn the shaft. I don't know if you ever played with those things. It looks like you spin it and it's got like a propeller on the top. That would be an opposite. It'd still be a wheel and axle, but you're turning the small thing. It's a distance multiplier in that case. That's where the mechanical advantage is going to be less than 1. All of these examples down here, these mechanical advantages are bigger than 1. You're getting big force out, but you have to exert large distance. Wheel and axle ideal mechanical advantages, it's the diameters. So you've got a large diameter, which in this case is 20 inches, and a small diameter in this case, which is 6 inches. It just depends on which one's being driven. So here's the question says, what is the ideal mechanical advantage of the axle? If the axle is driving the wheel. So we are exerting the effort on the axle. So when you do the whole I'm a deer, we're exerting our efforts on the axle. So if the axle is driving the wheel, that's our effort. So we're going to put the axle in for the distance. So it's going to be 6. The resistance is going to be 20. And 6 divided by 20 is the same thing as 3 divided by 10. So ideal mechanical advantage would be 0.3. Now you can switch that around, and you can have the wheel drive the axle. So that means that you're turning the wheel, so the distance that you exert would now be 20. And the distance of resistance is now going to be 6. So 20 divided by 6, so that's 3 and 1/3, so 3.3. So 0.3 and 3.3. Those are the ideal mechanical advantages depending upon which one you, the user, are exerting your force on. Your actual, am I free? What is the actual mechanical advantage if the wheel is driving? So it looks like we're putting our force here. So the force of exertion is 70. I have a hard time figuring out these numbers sometimes, but if I'm exerting 70 pounds, that's the exertion. That means the other force, 200, that's the one that's going to be the resistance. So 200 divided by 70, oh gosh, that's like 20 divided by 7. So it's like 2 6/7. 2.86. So that has an actual mechanical advantage of 2.9. I don't know if they flip it around on us. Yep. Oh, no, they don't. They say, what's the efficiency? So if the efficiency is going to be the actual divided by the ideal. So the actual mechanical advantage, 2.9. And the ideal mechanical advantage, is 3.3. Now remember, your efficiency can never be more than 100%. So if you go to try to guess, okay, which number do I put in there? Was it the 0.3 or the 3.3? You know it's got to be the 3.3 because it makes it less than 100%. So 2.9 divided by 3.3 turns out to be 88%, which isn't bad. There are far worse machines in this world. So that's 88% efficient if this is the case. On to our next one. A pulley. What a pulley does is it changes the direction of the force. For instance, my physics people, you're going to know that, let's say you're lifting like a load here, and this is pulling down with 1,000 pounds. And we can use pounds in engineering. We don't use pounds in physics. But so that means that this cable up here, it's exerting 1,000 pounds in that direction. So the cable just changes the direction of the force. So you're, instead of being straight down, now you're pulling on it in that direction. You're just changing the direction of the force. So pulleys, there's a couple of different types of pulleys. First one is a fixed. That's probably what you're most familiar with, putting a pulley up in the ceiling, taking a rope, putting it over top of it, pulling on it. So if this weighs 10 pounds, you got to pull with 10 pounds to make it lift off the ground. Now, you're probably going to have to actually pull with more than 10 pounds to overcome friction and things like that. So not quite true to life, but very close. The other type of pulley is called a movable pulley. So here you could tie the rope to the ceiling, go underneath the pulley, and then lift. And you'll notice, physics people, that if you have a 10-pound weight, so you got 10 pounds pulling you down, each of these ropes will exert 5 pounds, so 5 plus 5 equals 10. You have 2 ropes supporting your load, so they carry it equally because it's in the center right here. That's a movable pulley. So this one here has an ideal mechanical advantage of 1. This has an ideal mechanical advantage of 2. To find the ideal mechanical advantage of a pulley, a really complicated system, all you have to do is count the number of ropes. So the ideal mechanical advantage, it's just the number of strands opposing the force of the load. So here's a 600-pound motorcycle, and you've got 1, 2, 3, 4 ropes that are holding it up. So this has an ideal mechanical advantage of 4. So in theory, you'd only have to pull 150 pounds to do that. Again, you're going to have to do more because of friction, but in this case, look at, there's 4 ropes, so that's 4 to 1. Over here, this is 2 ropes. See how this rope and this rope both oppose the so this has an ideal mechanical advantage of 2 to 1. This one is not opposing that. It's not supporting it. This pulls down, that also pulls down. They're not pulling in opposite directions, so it's not supporting that load. Compound machines. So with a compound machine, all you have to do to find the mechanical advantage of a complicated machine is you multiply together all of the other mechanical advantages. So in this case right here, it looks like we've got a lever and we've got a pulley. So we're going to multiply the 2 mechanical advantages between them and find the mechanical advantage of the whole. So the first thing I'm going to do, it just says mechanical advantage. I'm guessing that it wants to know the ideal mechanical advantage because it's not telling me forces. If it gave me forces, then I could maybe argue, which one do you want me to find? Is it actual or ideal? But because I don't know how much weight we're talking about here, I have to use ideal mechanical advantage. So the ideal mechanical advantage total is going to be equal to the ideal mechanical advantage of the lever multiplied by the ideal mechanical advantage of the pulley. Now, the ideal mechanical advantage of the pulley is pretty easy. It's just 2. You count the number of ropes that are supporting the load. The ideal mechanical advantage of the lever, a little bit trickier. This is a second-class lever. It's like a wheelbarrow because you've got your load here in the center, and then you're lifting on the other end. So remember, it's dE divided by dr. I'm a deer. So the distance that I'm exerting is 12 feet. The distance of resistance is 4 feet. So that's going to be 3. So 3 times 2 is equal to 6. So the ideal mechanical advantage for this compound machine, this machine that has more than one simple machine, has an ideal mechanical advantage of 6. Here's a pulleys in combination. I could probably tell right now if this is my load, 80 pounds, and now I'm pulling up here with 10, that looks like a mechanical advantage of 8. So let's check it out. So right here, here's a movable pulley, and this has a mechanical advantage of 2 to 1. Here's my next one. That also has a mechanical advantage of 2 to 1. Again, I'm just multiplying these together because I've got them in combination. It's like a complex machine that we saw in the problem previously. Another 2 to 1. 2 times 2 times 2 is 8. And that's why you're seeing this being 80 and it's being pulled with 10. Now again, you probably have to pull more than 10 because of friction and all these pulleys. The line is going to stretch a little bit. They give off noise and you lose energy in that way. Let's see here. What is the actual mechanical advantage of this pulley system? So, am I free? So you take the force of resistance and you divide by the force exerted. So here's our 2 forces. The one that I exert, I'm going to exert 230 pounds. So that goes in the denominator. And then my resistance, that's 800. So I take 800 divided by 230, and I get 3.48. Is my actual mechanical advantage. Now remember, it's supposed to be 4. So I'm losing some to friction, so it may just ask me what's the efficiency. Yeah, it is going to ask me the efficiency. The efficiency of this thing is going to be the actual divided by the ideal. So 3.48 divided by 4, and you get 0.87. 87%, again, not bad. So, 23%, 13% of your inputted force leaves you as friction. Some common misconceptions with pulleys. It does matter, like the angles. Back to physics, when we talk about vectors, if this thing's pulling at 46 pounds, what it really means is it's pulling up at 40 and over this way at like, I think 22. That would be, using Pythagorean theorem, a squared plus b squared has to equal c squared. So that means that this one's also pulling up at 40 and this one's pulling to the left at 22. So you're pulling up at 80, right? And then you're pulling down at 80. So that's in equilibrium. You're pulling to the left at 22 and you're pulling to the right at 22. So it takes trigonometry, it takes the Pythagorean theorem, sine, cosine, tangent to be able to figure that stuff out sometimes. So just be aware that when you get multiple things pulling at angles, it's not always as straightforward as you think. And then another one is when does the effort one actually count? Only if you have a movable pulley, again. So you have to be, if the resistance is pulling in the same direction. That's it. That's our kind of tour of wheel and axle and pulleys, how to find their actual mechanical advantage. Am I free? Forces. And ideal mechanical advantage, I'm a deer, distances. And with pulleys, you just count the strands. It's pretty straightforward and kind of nice. All right, thanks for watching.